My hypothesis is, if I change the length of the straw and make it shorter, I will be able to make the pitch louder and the frequency higher. The shorter I cut the straw, the louder the pitch and frequency will be. The independent variable, or the antecedent variable, that is manipulated or controlled is the length of the straw. The dependent variable, or the consequent variable, that we measure to assess the outcome is the pitch and the frequency of the straw. Throughout the semester, I have learned that a sound wave is produced by a vibrating object. We also learned about resonance and how every object has a natural frequency, a tendency to vibrate at a particular rate. When you vibrate something at its natural frequency, it resonates, meaning that the vibrations build and grow more extreme. The oboe straw is a great example of this phenomenon and resonates when sound waves bouncing back and forth inside make a special pattern called a standing wave. I based my hypothesis off Lab 7, where we had to take 2 empty water bottles or soda bottles, fill them up with water, and blow air horizontally across the bottle opening and try to make it whistle. The pitch of the whistle depended on how much water was filled in the bottle and how much empty space remained. The shorter the air column, the higher the frequency. I figured that because this happened to the bottles, the same thing would happen to the oboe straw that I created. I wanted to create an instrument that changed frequencies when there was less airspace or when the instrument was cut shorter. This slide is about how my instrument was constructed. My instrument was very simple to construct, and the nice thing about this instrument is that you don't need too many supplies and it's pretty easy to make. So the materials I used were a plastic straw and scissors. First, I took the straw and flattened one end of it. I then cut off the 2 edges. This gives the straw a nice and pointy angle for sound to be created. I then put the cut end of the straw into my mouth and made a seal with my lips. I then blew into the straw. You will probably have to experiment with blowing harder and softer while biting down with different amounts of pressure until you make the straw sing. The beveled lips that were cut and flattened act as a reed for the instrument that I created. When you blow into the reed and get it vibrating, you send pulses of compressed air down the straw, causing the air in the tube to start vibrating too. Hi, so this is my video demonstration for my oboe straw. This is what it looks like. It's just a straw that's purple, and this pointy end acts as the reed for my oboe. I just cut off 2 points with the scissors, and this is what it sounds like when it's long. And this is what it sounds like when it's cut and made shorter. So as you can see, the shorter straw's pitch is a lot higher than the longer straw. Here are my measurements of the long straw. The time waveform shows a complex periodic wave. A complex periodic wave is tonal, having a distinct pitch. I also see on the FFT spectrum that there are multiple evenly spaced lines, which also tells me that this is a complex periodic wave. I used Audacity to measure the sound of the long straw. When I look at the FFT spectrum, I can see that the fundamental frequency is 312 Hz. The second format is 619 Hz, and the third format is 922 Hz. I also calculated the frequency by measuring the length of the long straw in centimeters, which is 21. I then converted this measurement to meters, which is 0.21. I then took the speed of sound in air, which is 344 meters per second, and divided it by 0.21, and that was equal to 1,638 vibrations per second, or hertz. Here are my measurements for the short straw. This is a complex periodic wave because I can see multiple harmonically related sine waves and a line spectrum with multiple lines. As you can see, the time waveform looks a little different than the long straw. There is more space being taken up on the time waveform, which tells me that the sound is louder. When I look at the FFT spectrum, I can see that the fundamental frequency is 518 Hz, the second format is 1073 Hz, and the third format is 1576 Hz. What separates each peak is the fundamental. I also calculated the frequency by measuring the length of the short straw in centimeters, which is 10.7. I then converted this measurement to meters, which is 0.107. I then took the speed of sound in air, which is 344 meters per second, and divided it by 0.107, and that was equal to 3,214 vibrations per second, or hertz. Here are my results of the long straw and the short straw. This is a comparison of the two fundamentals. As you can see, the long straw has a much lower fundamental frequency than the short straw. The long straw's fundamental frequency is 312 Hz, and the short straw's fundamental frequency is 518 Hz. The frequency of the long straw is also much lower than the short straw. The frequency of the long straw is 1,638 Hz, and the frequency of the short straw is 3,214 Hz. This tells me that the exact note that I heard when I blew into the straw oboe depends on the length of the straw. When I shorten the straw, I also shorten the wavelength of the standing wave pattern, which therefore increases the pitch of the note. My hypothesis was correct in that changing the length of the straw made the frequency and the pitch higher. The frequency of the straw depends on the length of the straw, and they are both inversely related. The pitch of the sound is higher with a smaller straw because the air column inside the straw is shorter, and the pitch of the sound is lower with the larger straw because the air column inside the straw is larger. From this project, I gained a clearer understanding of acoustics and how sound is reproduced in instruments, specifically oboes.